Welcome to The Explainer. Today, we're decoding a device that, let's be honest, you probably walk past every single day but literally never think about. Well, until the lights suddenly go out, right? We're talking about the circuit breaker. We're going to look at it not just as a basic safety switch, but as this absolutely fascinating, highly crucial mechanical device. It's the silent guardian essential for everything from keeping your home safe all the way up to protecting massive industrial operations. So here's our roadmap for today. 1. Introduction to switching devices. 2. Inside the circuit breaker. 3. How tripping actually works. 4. Relays and fault protection. And finally, 5. Types of circuit breakers. Let's dive right in. Okay, part 1. Introduction to switching devices. At its absolute core, a circuit breaker is what we call a switching device. Its main job is actually pretty simple. It either makes an electrical circuit, switches it on to allow current to flow, or it breaks the circuit to switch it off and stop that flow completely. You can really think of it as the ultimate gatekeeper of an electrical system. Now, what makes this device so incredibly powerful is its dual nature. Sure, a human can walk right up and intentionally flip the switch to manually make or break the circuit, but, and this is absolutely crucial, by receiving a specific signal, the breaker can also operate completely automatically. It's got a mind of its own when it needs to.
Which brings us to part 2, inside the circuit breaker.
To really understand how it operates, I want you to picture a giant mechanical drawbridge. Inside this device, we have a fixed contact that stays perfectly still and a moving contact that raises and lowers to bridge the gap. And this whole movement, it's controlled by the breaker's mechanical muscles, specifically a closing coil and a tripping coil. So here's how those muscles actually work to turn the power on. To make the circuit, you energize that closing coil. Once it gets power, the moving contact physically shifts, literally slams down to touch the fixed contact, and bam, they connect. The current flows, the circuit breaker is fully charged, and it is officially on. All right, part 3, how tripping actually works. Turning this thing off isn't just a gentle click. It requires a very specific mechanical sequence. You energize the tripping coil and our drawbridge raises. The moving contact is violently pulled away from the fixed contact. That physical connection is instantly broken, the current flow is interrupted, and the breaker is off. And hey, you can totally trigger this manually too, which is exactly what you do to safely isolate the power if you needed to do some maintenance. Moving right along to part 4, relays and fault protection. So this begs a pretty big question. How does the breaker actually know when to trip automatically? Think about it. If no one is standing there to flip the switch, how on earth does it sense danger? Well, it's because circuit breakers never really work alone. They're paired up with these things called relays. You can think of the relay as the brain constantly monitoring the system, while the breaker itself is just the muscle, patiently waiting for a command. That relay watches continuously, 24/7, for sudden, highly dangerous electrical abnormalities. It's constantly looking for an overcurrent, way too much power surging through the system. It's looking for undervoltage, a sudden short circuit, or maybe an earth fault. The specific type of relay really depends on your exact setup, but its job is always the same, to stand guard. This creates a brilliant automated safety loop. The split second that relay detects a fault, it fires off a signal to energize the tripping coil. Those contacts violently separate, and boom, the circuit trips. The whole drive is instantly protected. But here's the kicker. You can't just flip it back on. A human must physically go in, investigate the problem, clear the faults, and only then can the breaker be safely reset back to a ready-to-start state. And that brings us to our final section, part 5, types of circuit breakers. Because electrical power loads can scale so drastically, the breaker technology has to scale right along with it. For everyday stuff, you have the common MCB, or miniature circuit breaker. But scale up to heavy industrial environments, and you're going to rely on an ACB, which is an air circuit breaker, a VCB for vacuum circuit breakers, or even an SF6, which utilizes sulfur hexafluoride gas. The defining choice here always comes down to the specific application and the running current range of your unique system. To wrap up this explainer today, I actually want to leave you with a bit of a brain teaser to test what we've just covered. Okay, so both an isolator and a circuit breaker are fundamentally designed to make and break a circuit. So what is the actual fundamental difference between a circuit breaker and an isolator? I'll leave you to think about how they might operate differently when put under serious pressure. Thank you so much for joining me on this explainer. Keep exploring, stay curious, and we'll see you next time.